What if I told you that no matter how high you fall from, you can only go so fast? Imagine stepping out of an airplane at 30,000 feet. For a moment you accelerate, the ground rushing closer. But then, something incredible happens. Your speed stops increasing. You hit an invisible wall, a natural limit. This isn't magic, it's physics. This ultimate speed is called terminal velocity. It's the maximum speed an object can achieve when falling through a fluid, like air or water. It's a fundamental concept that shapes our world in profound ways. At its core, terminal velocity is a battle between two forces. Gravity pulls you down, constantly trying to accelerate you. But as you speed up, another force pushes back: air resistance. Air resistance, or drag, increases with speed. The faster you go, the harder the air pushes against you. Eventually, you reach a point where the upward force of air resistance perfectly balances the downward pull of gravity. When these forces are equal, the net force on you becomes zero. According to Newton's laws, if there's no net force, there's no acceleration. You continue to fall, but at a constant maximum speed, your terminal velocity. This speed isn't the same for everything. A feather, with its large surface area and low mass, quickly reaches a very low terminal velocity. A bowling ball, dense and streamlined, will plummet much faster. Your shape, size, and mass all play a critical role. A skydiver falling spread eagle presents a large surface area to the air, creating more drag and a lower terminal velocity. They might reach around 120 miles per hour. But if that same skydiver tucks into a dive, becoming more aerodynamic, their terminal velocity increases dramatically. They could exceed 200 miles per hour, slicing through the air with less resistance. This principle isn't just for daredevils. Think about raindrops. If they accelerated continuously from the clouds, they would hit us like bullets. Instead, they reach a gentle terminal velocity, thanks to air resistance, allowing them to fall as soft, life-giving showers. Parachutes are the ultimate demonstration of manipulating terminal velocity. By deploying a massive canopy, skydivers drastically increase their surface area, creating immense drag. This reduces their terminal velocity to a safe, survivable speed for landing. But here's the truly mind-bending part. Terminal velocity isn't just about falling down. It applies to any object moving through a fluid. A bullet fired straight up will slow down, stop, and then fall back to Earth. On its descent, it too will reach a terminal velocity. And what if there were no air? In a vacuum like space, there is no air resistance. An object would accelerate indefinitely, faster and faster, until it hit something. The very existence of terminal velocity is a testament to the pervasive, invisible presence of our atmosphere. It's a profound reminder that even in the most chaotic descent, there's an ultimate limit, a natural equilibrium. The universe, in its infinite complexity, always finds a balance, even in the act of falling.